Okay, guys, good morning. I'm gonna stop sharing my screen right now. I decided to start the morning off with some music. I thought it would be fun and entertain me and you while we're waiting for the discussion to start. I hope you like it, and if you have any suggestions for the music to play, for music to remove, feel free to message me and join in the morning to request songs. So for the second week, we're going to go over some basics of algorithm analysis, and I'll consider it, Theodore. We'll have a vote. We're going to go over some basics of algorithm analysis and how to write pseudocode. Let me start the presentation. Let's see. What do you guys see? Okay, you guys see the right thing. Gee. Let me just organize my screen so I can see all of you and the chat. Okay, good to go. The first thing that we're going to talk about is the time complexity. So I'm just going to start right off. Oh, one thing before I get into actually teaching this. If you have any questions about algorithm analysis, please ask right away. Do not worry about the time or if the question is embarrassing or anything, because this is going to be really important for you to understand. Ask me in a private message. Ask me to stay later with you if you need any help. But this is going to be really important, and we're going to ask you about this in almost every assignment that you have. So I know that the second part of the presentation is pseudocode writing, and yes, you will have to do that too, but pseudocode writing is something that you can read the presentation on your own time and just try out different things, try to write some functions in pseudocode just to get the practice of. This is actually going to be the important part. So yeah, feel free to ask questions. Please do if you don't understand anything. Okay, let's see. Yeah, so time complexity is essentially the amount of time taken by an algorithm to run. It's usually a function of length or of the length of the input, which I know Dr. Aman, or I know you in the lectures, it was mentioned that the time complexity does not depend on the input, and that's true. It is still a function of the behavior of the input, if you will. So there are three typical methods of growth that we talk about. I'm sure you've went over the literal time complexity of measuring the time, etc. in the class. We're just going to talk about the growth analysis functions. So the first one is going to be the big O notation, and that denotes the asymptotic upper bound of the function. So that means that we're looking at the absolute worst way that a function can behave in. So the absolute highest value it can take, or the highest growth rate, if you will, derivative. The way you write big O notation is you put capital O, and then in parentheses you put the function of which you're looking at. So the given function g of n. Usually we'll be looking at something like a function of n that looks like a logarithm of n, or just n itself, n squared, etc. And you're gonna put those in the parentheses. And yeah, this is the pronunciation. You say big O of g of n, or the order of g of n. The second notation is going to be the omega notation. It's the asymptotic lower bound of a function. So it's the absolute lowest growth rate that your function can have. It's not particularly useful for us because we're looking at optimizing the code in the, well, we're looking at optimizing the code in the average case a lot of times, but what we want is to optimize it when it's behaving, when we think about how it behaves at the worst moment. So like, we don't really care about the lower bound because it doesn't tell us much. And I'm gonna tell you a little bit about that more. I'm just gonna go over the third way we can measure this, and that's the theta notation, which is the tight bound. So you consider the tightest lower and upper bound of the function. So the reason we don't actually use the omega notation is, for example, if you have let's say an algorithm that has, for example, three nested for loops, and they all execute in n times. The big O notation of that will be n cubed because the innermost loop is what actually executes the code, and it's run n cubed times. It runs n times for the first element of the second loop, and then it runs n times for the first element of the first, I guess, loop, whatever. I think you understand that. If you don't, we'll go over it again, but don't worry about it. So 3 nested loops, n cubed. It's still omega n though, because n cubed grows faster than n. So the lower bound is still n. But for example, consider that we have only about 100 elements in an array. That's not usually a lot for, or n iterations of the loop. That's not usually a lot for the current computing standards. But let's also say that the innermost loop, each iteration executes in 1 second, which to us it's fast, to computers it's slow, but suppose that you have some big game that you're working on, and you have those 3 nested loops, and it takes 1 second to iterate through the innermost loop. With n being 100, so 100 iterations at each layer, you get about 1 million seconds to execute all of those, which is about 17,000 minutes, and that's 278 hours, and that's about 12 days. So for just 100 iterations, you'd need 12 days to execute something that is omega n, which is a linear growth rate in the lowest bound. So it's not very useful for us, because how can we measure that or how can we measure the amount of optimization necessary for something that we have only the lowest bound for? That's why we consider big O, because we wanna see how bad can our code perform, and can we make that better? Let's see, what else do we talk about here? Oh yeah, just a quick example. We're gonna talk about the rules of determining how to simplify the big O notation functions. But this is just an example to let you know that, for example, if g of n is 5 times n squared plus 4n plus 2, we're gonna take the leading element, or the leading degree of n, I guess, in this case, to be our central measure. We are also going to talk about, if the slides will switch. Yeah, okay, so talking about the visualization, we have big O, which is the upper bound. So when you set up function g of n, inside this big O of g of n falls every function that grows slower than g of n. So everything in this yellow section here is going to be your O of g of n. If you consider omega, then everything that grows higher than our g of n, everything in the yellow in the middle graph, is going to be your omega g of n. And then theta is the tightest interval or bound on both sides. So you have the upper function, which is going to be your g of n, and usually determined by some constant, and then the lower bound your g of n, which is also determined by some lower constant, and your function f of n, if it's theta g of n, is going to be somewhere in between those two. Oh yeah, the link at the bottom of these slides, the slides should be available for you. If they're not, I'll make them available for you once we're done with the discussion. But if you need more resources on this, feel free to check out this link. Now, best, average, and worst case time complexity. Usually we might ask you to okay, sorry, I'm reading the question in the chat. And the previous slide. So here, okay. Oh, you mean N0? Okay. So N0 is some starting point that we measure from. So for example, in all of these, when you look at N of 0, this is where we can, with certainty, determine the growth rate of f of n. So for the big O, okay, for the big O graph at n0, our f of n starts to actually be bound by g of n. Before n0, we have this unpredictable behavior that we're not entirely sure of, or we can't, or it doesn't have a bound, etc., or it doesn't just fall under g of n. So we set up this n0 as a starting point where we can actually measure the growth rates / bind the growth rates, etc. Is that clear? Okay, great. So for the best, average, and worst case time complexities, we might ask you to do all of those. We might ask you to just do one. So be sure to read the questions carefully when we ask you about this. For each of those, you have to consider that the complexity will always be independent from the input size n, but the type of input that we're giving an algorithm might determine the complexity itself. So in the case of sorting algorithms, for example, where which is the example we're given in the slides, the way you arrange data that you're trying to sort is going to determine the behavior of your algorithm. So how much does it actually need to do? So the best case you would have for an algorithm that is that behaves something like bubble sort, you would have an array that is already sorted, for example. You would, in that case, not need to do anything, and the algorithm might just run through all of the elements once, and that will be the complexity of O of n. But if you have an array that's inversely sorted, so reversely, for example, if you're trying to sort your array from lowest to highest element or number, if you sort them reversely, so you start with highest and then they slowly decrease to the lowest, and you try to sort it with a bubble sort, that will be your worst case time complexity, and it will have to do the most swaps in the algorithm or in each iteration of the algorithm. That's what you're going to have to consider when you're writing your own code, when you're reading someone else's code. How will the type of input that you're given determine the behavior and the complexity of your algorithm? This is some comparison. We generally do not like algorithms that are in the red area, or growth rates that are in the red area. So n factorial, horrible, grows horribly fast. We don't want that. Optimize it any way you can. 2 to the n2, so any actually exponential function, it's pretty bad. any polynomial of n of a higher degree than 1, bad. And then we have n log n, that's going to be a common one for you guys, but it's not bad, it's not good, it's okay. And then we have O of n, which is the linear growth. That one's sort of kind of fine. Maybe you can optimize it. And then you have O log of n and O of 1, which are usually the best ones. You strive towards those, even if it's impossible to do. So far I've talked about time complexity, and that is obviously talking about the amount of time that an algorithm might take to execute an algorithm, or to process the input given to it. Space complexity, however, describes the amount of memory that an algorithm takes to process the input given. So how many variables does it store? Does it copy them? Does it just operate in place? Does it create new arrays, or just operate on the existing array for sorting algorithms, etc.? That's going to be your space complexity. You might be asked to differentiate between them, so don't make mistakes on those two, or don't swap them. And be sure to practice both. It's important. They are determined differently, strangely enough, in a sense that you don't look at the same things in code to determine both of them, even though they'll both be big O notation. So next slide is our first poll question. I actually did make a poll for you guys this time, and I'm just gonna start it now. There we go. Can you guys see the first question? Anyone in the chat? Oh, that's okay. You'll still have to look at the slides to answer them. So just answer them one by one, and then I'll fix that later on. So the first question that we're gonna answer, or attempt to answer, is for the code given in this slide, what is the best case time complexity? And the code that we're given is actually a bubble sort. So if the input array has only one element in this case, what is the best case time complexity going to be? O of 1. You don't have to answer any of the other questions. Just answer the first one. Come on, guys. I have on the poll. Brody, right? That's what you told me last week. Oh, really? Dang. I really tried to make this one. Gosh darn. You know what? No. Type it in the chat. True or false? I'm just gonna end this. Make it faster for us. See, now I would really appreciate it if you guys typed true or false and not just F, because that might be the F in the chat for the poll, honestly. I don't know. Okay. So the answer to that one is false, because we don't take into the consideration the exact size of the input, the exact size of n. So yes, if you plug in n, it's gonna be O of 1, but it doesn't grow with the rate of O of 1. since bubble sort actually does the whole thing in here where you have the panel. You have one for loop and then you have another for loop, and they both go to some grow with some respective n. So you're gonna have technically n squared depending on how you sort the array. Yeah, so that is why in this case our answer is false. Even if we have one element, we talked about it in the previous slide, the best case for this algorithm is going to be if we have a sorted array, it will still, no, it's n squared in this one, or in the best case it's going to be O of n, because it's still going to have to run through all of them to check if that element is in the right place. Here. Are we good on this one? I'm just going to move on. It's okay. Now we have a couple of rules for the asymptotic analysis. These are going to be the four rules that you're going to have to think of every time you do this. You're going to have addition. You're going to drop the constant multipliers. Going to drop the lowest order term. And you're going to have to consider each input variable that is different or grows at a different rate. So the first rule is going to be addition. If you have something like this, for example, where we have two non-nested for loops, one executes until I is n minus 1, the other one until j is m minus 1. The time complexity of this algorithm depends on both n and m. So you're going to have to reflect that in your big O notation. So because they're not nested, they're just going to be added because you execute this one in some O of n. God, that's an ugly n. In some O of n time, and then you're going to move on to the next loop and you're going to execute this one in O of m. And so total time between entering this curly brace and exiting through this curly brace is going to be O of n plus m. Are we clear on that one? So if they're parallel, they're not nested, you execute this one first and then you execute this one first. You just add them. We good? Thumbs up in the chat for this one. For rule number 1, please, someone. Nice. Okay. Dropping the constant multipliers. So last case we had n here and m here. Now we have both executing with n. Once again, we have first for loop executes in O of n, second one executes again in O of n. So we apply the rule number 1 and we say O of n plus n. However, we know math. We're at this point all good at adding two numbers, and we can say that this is O of 2 of n. However, the constants don't necessarily contribute. They do contribute obviously to the growth rate, right? We've established that in the graph slide. But when you talk about the growth rate, whether it's gonna for a very large n, consider 2 trillion or 1 trillion, it's not, the differences between execution times are not going to be very different if you have 2n or just 1n. They're still going to behave the same way. So we're just going to drop the constants. We're going to ignore those. If you have a constant multiplier, just ignore it. Don't think of it and just write O of n. Okay. Good on this one, thumbs up. Responds, okay. Brody, I count on you. You've been typing the most. Nice, thank you, Lily. Rule number 3. We've talked about it already. Good job, Brody. Yay. We've talked about it in rule number 1 already. But if you have different input variables that you cannot say grow the same way. So for example, let's say that you have a string and the length of the string grows at the rate of n. So let's say that our string length is n. And then you have some array that has possibly the length L. We don't know how those two relate. You know, the string can be much longer than the array or vice versa. So we cannot actually simplify it. We cannot just drop one, and we have to keep both of them if we think they grow at the different rates. So n here, L here, we keep both of them. And it's going to be the same way even if we nest the loops. If we cannot establish a relationship between n and L, you have to keep both of them. And rule number 4, you're going to drop the lowest order term. If a function or if part of your code runs much slower or obviously takes more time than some other part of your code, for example, these 2 loops, you won't necessarily care how fast it takes to execute the slowest one because the faster one, because the slower one is the one that determines it. You're still going to be waiting for the slower one, even if the faster one can execute before that. So you're going to drop the lower term. In this case, logarithmic function grows slower than the linear function. So we're just going to lose it. We're going to drop it. We don't care about it. We simplify it to O of n. We good on this one, or should I go over it more? Okay, nice. Thanks, Lily. We have I wouldn't necessarily say that, Sai. If you cannot exactly say that m and n have some relationship other than m being greater than n, I would keep both of them. In this case, I don't know why he gave you 2 different variables, because m and n can be completely different and they might both contribute as you said it. I wouldn't necessarily drop functions with different variables, but if you had n plus log n, I would just drop the log. Okay, poll question number 2. Just drop in the chat which one you think is right of these 4. So what is the time complexity of this algorithm? We have a for loop that executes n times and is incremented by some constant c, and it has some O of 1 expressions here. Or we have a for loop that starts at n but decrements by the same constant. Oh, you're speedy. Nice. Okay. I'll still give you time. I want to see as many responses as I can. Good. This one was easy, right, guys? It was fine. It was okay. Of what? Of n. Sorry, because you increment by a constant. The c can be 1, 2, 3. It doesn't matter. You're constantly incrementing I until it reaches n. So, or decrementing it, it doesn't matter. It's still going to be O of n. Next question. What is the time complexity of this algorithm? So we have the first for loop, it goes until n, and is multiplied by some constant c each execution. And then we have the second loop that will still run n times, but is divided by some constant c until it reaches a number greater than 0, or and reaches the smallest number close to 0. Which of these? Let's see. Oh. Come on, we have Brody and Jaden. They're active. Nice, Theodore. Yay, sign. Go, Nico. Is this one harder, guys? Okay. So, the answer is log n. Yeah. We don't necessarily specify the constant of the logarithm or the base of the logarithm. That's, yes, we did. You did slay. You're right, Jade. But because I is multiplied each time, you're gonna have something like starting with 1, you're gonna have first iteration 1. That's not where I wanted it to go. Here, 1. The next iteration you're gonna have c, then you're gonna have c squared, then you're gonna have c cubed, etc. And that you're gonna reach n or some number, some power of c that is really close to n, but higher than n, in log base c of n. And that can be seen in the second one a little bit better, because you have n and then you divide it by c, and then the next one's going to be like n over c squared, etc. And this is basically logarithm base c of n. Yeah? Are we good? We have more examples. There's about, you saw 10 questions. Next one. What is the runtime of this code? We have 3 for loops. First one, or no, well, yeah, 3 for loops. First one runs until some length a, suppose that length of array a is a. The second loop runs until j reaches the length of array b, which is gonna be some b. And then the third one runs until k is, what's that number? 100,000. What is the complexity of this code? And the print ln is of 1. Type it in the chat, guys. Yay. Okay. Great job. Good job. You did so well. You implemented that rule number 2 so good. Okay, so for people who said n squared, yes, you could technically do that if you knew the relationship between a and b, but we don't give you any context here, so I would honestly just keep it as a times b. And because the last one is a constant, we don't care about that. So we just drop the 1,000. So yeah, of a times b. Good job, guys. Yay. Next question. Oh yeah, I talked about that. It's okay. So we have 2 for loops. And this one's tricky, guys. We have 2 for loops. First one runs from n to 0 and decrements I by a constant each time. The second one, that's the trick, goes from 0 to I at each iteration and is incremented by a constant. Low-key maybe D. Okay. Ooh, spicy. I like it. Lily and Endrit, did I pronounce your name right? Endrit? Nice. Okay. So you two got it right. Do any of you want to explain how you got there? High key A, yeah. Yeah, Jake. Okay. I am just gonna quickly go over this. Oh, spicy, but I am. Oh, I'm sorry, guys. That was my bad. I'm sorry. Whoever said n squared, you're right, because I wasn't looking at how I is growing. I'm really sorry, guys. We're gonna have a spicy one next. Okay. Sorry. Good job, Brody. That's the thing. It is growing by n squared because we linearly decrease I. So you have something like first execution of for loop of the inner for loop is gonna go from it's gonna be executed n times because I is n. I'm sorry, guys. I'm sorry, but you'll see what I mean in the next one. I promise I'll make up for it. I'm sorry. The first execution of the for loop is going to run n times, and then we're going to decrement I by 1, so we're going to have n minus 1. And j is going to go then n minus 1, and then it's going to go n minus 2 plus etc. until we reach something like 0. Right? And it's going to have n appear here basically n times because this is n minus n. So we have n times n, and that's going to be n squared because I is decreased linearly. That's the trick. The linear part. We're just decrementing by a constant. This one. This is my question. Jaden, good job. That was a quick answer. You were so ready for it. Now we decrement I by 2 every time. So you divide it by 2 every time of the execution. D, indeed. Okay, indeed. That would be a nice pun if I should have made it when the D was actually the answer. I'm sorry, guys. I tricked you again, I guess. I hope not. But the answer this time is O of N. And Lily, I think that's what you were thinking of last time. But yeah, so this time what we're gonna have is the first iteration of the loop. We're gonna run it n times of the innermost loop because j is gonna go from 0 to n. And then we divide our I by 2. So the next iteration is going to be something like n over 2, right? And then we're going to have something like n over 4, etc., etc. Now, everyone who said D, I kind of see where you're going, where you're coming from, or where you were going, considering that we have this divide by 2 each time. However, because J is not executed independently, we cannot say that you have some n multiplying the logarithmic function. Yes, indeed, Lily, you're right. This is it has an explicit formula, which is n times n minus 1, I think, over 2, or n plus 1. Or something like, it's something really stupid, and it's not this because that's quadratic. But it has some stupid formula, stupid easy formula that is. Lily, do you know the formula for this one? I know this is gonna be actually asked a lot, guys, so just know. I forgot about that. Okay, it doesn't matter what the formula is. The answer is O of n because it's gonna be some constant of n. Yeah, as n goes to infinity. You're right, guys. Lily sent the message, and I am going to give you the. Let me see where. I'm gonna have to stop sharing for a second, guys, to give you the access quiz, the access code for the quiz, and then we're gonna move on.